Okay, I just want to review with this first problem. All right, so the thing that we suggest is that you write down all the information given. Okay, the first information that's given there is 23 meters per second square, which tells you you're in using metric system, so you're going to revert to 9.8 meters per second squared as A. Okay, the launch angle is 30 degrees. The initial height is 10. We're after the time and then the range down. Okay, so we start off with, as always, our opening parametric equations in x and y as displayed here. We put in the information we have. Cosine 30, root 3 over 2. Sine of 30 is 1/2. So we're trying to find, okay, the maximum range here. The maximum range will be determined when it's in the air for the longest period of time. It's in the air. It's in the air until it hits the ground. It hits the ground when y is 0. So with y equaling 0, we've got a quadratic that we solve. We find 2 times. Okay. One's going to be negative, which we're going to throw out. So we'll look at that. And the other is going to be the answer, which we're going to find is roughly 3 seconds that it's in the air. So when 3 seconds in the air is thrown back here, we'll find the total displacement, which is about 60 meters. Okay. So here I've drawn it up for you. Okay. I put another parameter in here. Here's my there's my starting parametric equations here. Okay. Now I put another parameter in here for the angle just to show you some variations. At this point, the angle is set to 30 degrees. Okay. I've run this a little bit over. I know it stops at 3 seconds. I mean, we'll show you the 3 seconds and then show you why I went back to that. Okay, so I'm going to put it back to the 3 seconds. This is the parabolic. This is the object in motion right here. Okay, there it is in motion. Of course, it doesn't spring backwards like that, so we're going to go one directional. That's the object in motion. Okay, which you can see is in the air for that 3 seconds, so it hits the ground, and it hits the ground at that displaced value, that maximum range of 60 meters or thereabouts. Okay. When you went and solved that quadratic, you found you had another negative value for t. I think that's about negative 0.65, 0.67. So if I were to alter this, I'd show you that backwards value, negative 0.67, okay, which would be, as if it were launched from ground, although it is not. And when you're solving the quadratic formula does not know the application, does not know that the variable you're solving for is t. So you have to use your own discretion and intellect there to determine that. So we are then limiting this to 0 to 3, okay? Because that's the path. Now, here's the interesting thing, okay? So, and for this purposes, I'm going to come back and I'm going to change my, I'll let my parameter run up to 6 seconds, okay? Down here as well. Now, of course, running up to 6 seconds means that this thing is going to go into the ground, if you will, okay? Which of course makes no sense. But I've done that just so I could illustrate something for you, okay? So, so what we're going to do is we're going to see, okay, if we were to launch this thing at varying angles, which is our parameter down here, what is the net impact? So if we were going to launch it at a smaller angle. Okay, now of course we were at 30, and we see here our maximum range is about 60 meters. If I'm going to if I'm going to go at a lower angle, okay, you can see now at an angle of 20-degree launch, okay, with the angle of 20-degree launch, you can now see that I'm losing range. I'm losing range, okay? Um, and in fact, okay, and of course I'm losing hang time because uh, if you can see, this thing is hitting the ground right about at 2.4 seconds, okay? Now, if I were to take this thing at 0 degrees, okay, then that means I'm just shooting it out horizontally, like I'm throwing a baseball, okay? And to that extent, you know, um, to that extent, I have my absolute minimum range. My range is now, what, about 33 meters. My range is about 33 meters. And of course, my hang time here is going to be minimum. Um, and that's going to be roughly less than 1.5 seconds. Now, basically, if the angle is 0, if we come back up here and look at our working equations, okay, if our angle is 0, then the cosine of 0 is 1, so this just collapses to the velocity times time, all right? And the sine of 0 is 0, so that means this entire portion of the of that parametric equation is lost, which means, okay, we're down to simply looking at negative 4.9 t squared plus 10 as the parametric equation in y, which is effectively the same as if, okay, it is the same as if it were, okay, um, dropped from that height. So in other words, it spends as much time in the air um, going downward, okay, as it would going, okay, along this path, all right? And of course, even if I altered the velocity, I'd get more range out of it, but the time in the air would be exactly the same as if it were to drop straight down. And if it were to drop straight down, that is to imply that okay, there's only the influences of gravity acting on it, okay? So you bear that in mind. Now let's go and change this angle up again, okay? We were at 30. I'm looking to see if I can get more range out of this with a different launch angle. So 35 is giving me better launch angle. And of course, uh, 35-degree launch angle is giving me a better range. And of course, you'll see that I'm in the air longer as well, okay? 40, I'm getting better hang time, okay? Getting a hang time, and therefore I'm getting a better range, okay? Um, 45, 45 is, I'm getting even better hang time at a 45-degree launch angle, okay? Short of 4 seconds, okay? With a range about 62 meters or so, okay? 50, look what happens at 50, okay? I've got more hang time, but my range is not getting any better, okay? In fact, at 60, at a 60-degree launch angle, okay? At a 60-degree launch angle, I have a lot more hang time, but I've lost my range, okay? So that's what's going to happen. I mean, I'll get more hang time if I go up to an 80-degree angle, 80-degree angle of launch. I'm only getting, as you can see here, I'm only getting a a maximum range of about 20 meters, but I'm getting a hang time of close to 5 seconds. Okay, I'm getting a hang time of close to 5 seconds. So if I go to 85 or if I go 90, you're going to see nothing. Okay, and that's why you see nothing is because it's going straight up and straight down. Okay, it's going straight up and straight down. So um, you're not getting any uh, horizontal displacement. Your range is nothing because you shoot it straight up, it comes right back down. So just some things that you can learn, and you can use this playing around. And of course, you can alter these other input values, okay, to match the problem at hand. Just basically the only thing you have to change would be V0, and in fact, you could easily just add another um, parameter for that, okay? And so maybe in fact we'll just do that. Make this parameter V, okay? And likewise, we need to make that here as well, okay? And now we'll add a slider. We'll add a slider for V. We'll let V velocity run from 0 anywhere. Let's go up to about 100, and we'll just do that in steps of 5, okay? And we're then going to have to come down here and modify this equation now with that input as V and with this as V, and we are going to of course my velocity I uh, have to alter this because my step was 5, but we can do that on an individual basis. So we can go back to our our, our initial velocity of 23 here, okay, and the angle, of course, being 30. But then we could also play around with, see, we could also venture to see that we could get more range with a higher velocity, okay? More range with a higher velocity, all right? And we want to remember, if we're getting more range, then of course we're getting increased hang time. So you have those things to play around with, okay? The velocity, okay? Lesser velocity, less hang time, less hang time, less horizontal displacement, maximum horizontal displacement being the range, if you will. Okay, so I'm going to save this Desmos file, and I'm going to give you the link on that, and you can play with that at your discretion, and hopefully learn from it as well. Okay, so there you have it.